So, in the last lecture we just looked at locally compact Hausdorff spaces, and we saw that the space of continuous functions on such a space is a rich class. In fact, if X is large enough, it is an infinite dimensional vector space. And now we will look at certain linear functionals on this vector space and connect it with measures. So, this is a rather major theorem due to F Rees, it is called Rees representation theorem. So, I will not prove this theorem because the proof is somewhat long and it takes more time. What we do is we will state the theorem in full detail, look at some examples and look at its consequences, and then we will use the theorem to construct the Lebesgue measure on Rn again. So, we have already done one construction of the Lebesgue measure, starting with cubes and defining measurability using open sets and things like that. Instead, we will use a linear functional, and this linear functional is going to be the Riemann integral of f, and that will give a measure according to the Rees representation theorem, where certain properties which we have seen earlier like completeness, translation invariance, etc. will follow from the theorem itself, and more importantly we will have certain uniqueness properties of the Lebesgue measure which we will deduce from Rees representation theorem. Okay, let us start. So, going back to what we have done, X is a locally compact Hausdorff space and X tilde is one point compactification, and we can see C0x as a subspace of this. Okay. So, to complete, so let me add one more exercise here so that you get used to these spaces. These spaces are important spaces in analysis, and we will be looking at C0x later on, when we study complex measures. So, right now CCX is contained in C0 of x, and C0x, the space of continuous functions vanishing at infinity, is a complete metric space. So, some of these are sort of straightforward exercises, but if you are having difficulty with locally compact Hausdorff space and so on, you may assume that the x is the real line, or Rn, x is equal to Rn with the usual metric, Whatever I say will be applicable for Rn as well. Okay. So, most of this is, so a reference here may be perhaps apt. So, you can look at book by Walter Rudin, Real and Complex Analysis, Real and Complex Analysis. This is from the second chapter. Okay, so let us go ahead. So, CCX, so X is again a locally compact T2 space. CCX, all those functions with compact support, f from x to c, continuous, and support of f is compact. So, we saw that by Urysohn's lemma there are many such functions. So, this is generally a infinite dimensional space if x is big enough. If x is finite, we saw that this is just Cn. Okay, so there we don't bother too much about such spaces because they are already taken care by linear algebra. So, here if you look at CCX, this is a vector space. CCX is a complex vector space. Well, why is that? If I take f and g in CCX, then alpha f plus g, where alpha belonging to complex plane as scalar, will also be in CCX, right, because the support of this function alpha f plus g is contained in the union of, so maybe instead of writing it in English, let me write it in mathematics language, support of f union support of g. And this is of course compact, right, this is just union of two compact sets, so this is a compact set. So, support of alpha f plus g is compact, and so this would belong to CCX. Not just the sum, you can also take the product. If I take two functions in CCX, then of course f times g is also a continuous function and will belong to CC of x, right, because in this case the support is actually the intersection, right, support of f dot g, f times g, right, this is contained in the support of f, because both of them should be non-zero for the product to be non-zero, right. So, support of f, support of g. Okay, so that is about the space. Now, the space is a linear space, a vector space. So, we can talk about linear functionals. So, this is what we do in linear algebra. Generally, we have a vector space and we have linear maps, right. So, here we have linear functionals, which means that it takes values in the real line or complex plane. Okay. So, we look at CC of x. From CC of x to the complex plane. So, we are looking at complex valued continuous functions. So, our basic field will be complex plane. This is called a linear functional, is called a linear functional if it is a linear map. If lambda is linear. Okay, what does that mean? That is lambda of f plus g equal to lambda f plus lambda g, and lambda of alpha f equal to alpha times lambda f, right, where alpha is a complex number, f and g are in CCX, right. The vectors in the vector space are functions. Such a thing is called a linear functional. Well, let us look at trivial examples just to get used to it. So, let us take x to be the real line, okay, and I am looking at CC of r. Of course, there are lots of functions with compact support. You take any interval, you can draw a function which is supported there, right. You draw an appropriate triangle which is a continuous function. Okay. So, we define lambda to be to the complex plane by f lambda of f. So, lambda of f is a scalar, right. So, I should give you a number. Let us take f of 0. This is obviously a linear map because f plus g will go to f0 plus g0, which is lambda f plus lambda g, and if I multiply f with alpha, alpha comes out. So, this is obviously a linear map. Of course, you can take many other points, for example, so you can take, so let us say lambda 1 and lambda 2 you can take to be f of 0 plus f of 1 plus f of 2, etc., maybe f of k for some k, right. That is also a linear map. You can divide by this some number n, or you can put constants here, alpha 1, alpha 2, alpha 3, etc. They are all linear maps. They are all linear functionals defined on CCR. Well, what is the relationship between measures and these linear functional? That is the Riesz representation theorem, which I will state in full detail. But before that, let us look at this itself. How do you write f0 using a measure? So, define this measure, define delta naught, okay. Let us say on B of r. B of r, remember, is the Borel sigma algebra, right. Borel sigma algebra of r. So, delta naught is a measure. How is it defined? So, delta naught of A equal to 1 if 0 is in A. So, this is the Dirac delta supported at 0, 0 if the point 0 is not in A. Okay. So, anything which intersects A will have measure 1, otherwise it is 0. So, now if you look at the linear functional lambda, lambda of f to be f0, this is my linear functional defined on the continuous functions on compact support, right, to the complex plane. I can write f0 as integral over r f d delta naught. Delta naught remember is a measure. So, we know how to integrate this, right. Well, how do we compute something like this? We have done this several times. Notice that delta naught outside the point 0 is 0. So, I can discard that, right. So, let us compute integral over r f d delta naught. Well, this is equal to integral over r minus the point 0 f d delta naught plus integral over the point 0 f d delta naught, right. This is because they are disjoint and so integral adds up. But this is the first term is 0 because this set has measure 0, right. It does not intersect the point 0. So, delta naught of r minus 0 is 0 and this is just a single point, right. So, I will have f0 as a scalar coming out and the measure of the point 0 which is 1. So, that is just f0. So, f going to f0 is actually given by an integral. More generally, whatever example we have seen here, these are all Dirac delta at 0, 1, 2 and so on, and then you are adding up. So, if you integrate against that measure, you will get that particular linear function. Okay. More generally, if mu is a positive Borel measure on let us say R, it can be on a locally compact Hausdorff space. So, what is a positive Borel measure? Borel measure meaning defined on the Borel sigma algebra. Okay. Then with some property. Okay. So, positive Borel measure on R with the property that mu of k is finite for every compact k, okay, contained in R. Then the map, let us say lambda from CC of R to the complex plane, how is it defined? Lambda f to be equal to integral over R f d mu. Now, see, this makes sense, right, because f is a continuous function. So, it is Borel measurable. If I pull back an open set, I am going to get an open set which is in the Borel sigma algebra. So, f is measurable. So, I can integrate f with respect to the measure d mu. And this is finite because of this condition, right, because support of f. So, let us digress a little bit. Integral over r f d mu I can write as integral over support of f d mu plus whatever else is 0, because outside support of f is 0. So, I can forget this part. And so, if I take modulus, this is less than or equal to support of f mod f d mu, mu is positive and this is less than or equal to, I can take the L infinity norm of f outside, right, the supremum norm of f outside, because that is bigger than f, and what remains is the measure of support of f, but that is finite because this is compact and this condition. Okay. So, this is a perfectly well defined map and it is clearly linear because it is a integral is linear. So, this is a linear functional. Okay. So, that is a general definition of general collection of linear functionals. Now, what is important is that lambda is a positive linear functional. Lambda is a positive linear functional. What does that mean? That is if f is non-negative, then lambda f is also non-negative, right. Lambda f is nothing but the integral over r f d mu, and mu is a positive measure. So, if f is positive, its integral is also positive, right. f d mu is positive. So, positive functions are mapped to positive numbers, that thing is called a positive linear functional. Okay. So, any positive measure defines a positive linear functional, right, any positive measure with this property, that is important. Okay. So, on compact sets it has finite measure. The converse is called, so let me write down this as statement. So, any reasonable positive measure, so reasonable here means that mu of k is finite for every k compact, right, that is what reasonable here means, that any reasonable positive measure defines a positive linear functional on CCR. Well, I can change this to CCX, right, where X is a locally compact Hausdorff space, right, just like what it defines on CCR, it defines on CCX as well, integral of by, so by integration, right. So, any reasonable positive measure mu defines a positive linear functional by lambda of f equal to integral over x f d mu. So, what is the triple we are looking at? We have the space X which is locally compact Hausdorff and the Borel sigma algebra of X. What is the Borel sigma algebra of X? This is the sigma algebra generated by open sets of X, right, that makes sense, and we have the measure mu. Then this is the triple and integration is well defined, right. F is a continuous function, so it is measurable, right, continuous functions are measurable with respect to Borel sigma algebra, because when I pull back an open set I am going to get an open set. So, any reasonable positive measure mu defines a positive linear functional on CCX by integration. Okay. The converse of the statement is called the Riesz representation theorem. Converse is the Riesz representation theorem. Riesz representation theorem. So, we will denote it by RRT, Riesz representation theorem. So, let me state this in full detail, it is a slightly long statement. Okay. Riesz representation theorem. So, we start with a locally compact Hausdorff space, locally compact T2 space, and our object of interest is CCX. Okay. So, let lambda be a positive linear functional. So, that is, as of now, that is very important. We are only looking at positive linear functional on CCX. Then there exists a sigma algebra, M, script M, of subsets of X. So, it is a sigma algebra consisting of subsets of X. How big it is? It contains, which contains the Borel sigma algebra of X and a unique positive measure mu on script M such that now comes the statement of the theorem. So, we get a sigma algebra M and a measure mu which satisfies the following. So, 1 lambda of f equal to integral over x f d mu for every f in CCX. So, that is the important part. The most important part of the theorem is the first statement, that any positive linear functional on CCX is given by integration against a positive Borel measure mu. So, notice that everything makes sense because the right hand side is integral over x f d mu. F comes from a continuous function, f is a continuous function. So, it is measurable and I can integrate against mu. Well, we will see that mu has the reasonable property which we mentioned earlier. So, that is the second one. Mu of k is finite for every k compact subset of x. So, that tells me that the first one makes sense, right. The integral will be finite because of the second property, that is the reasonable property we mentioned earlier. 3. Now, you will see some things which are very similar to what you saw when we constructed the Lebesgue measure. Okay. So, keep those properties in mind and you will see that this is purely the abstract version of those properties. For every E in M, so remember M is the sigma algebra we have got which contains the Borel sigma algebra of X. We have mu of E to be infimum of mu of V where E is contained in V and V is open. So, this is simply the outer regularity. We had outer regularity for Lebesgue measure. And remember there was an inner regularity for certain sets. So, that continues to hold. So, let me write down that as well. If mu of E is finite, then mu of E equal to supremum over mu of k where k is now inside E and k compact, right. So, this is true for every E, well E has to be in M of course. So, but you have this additional condition that it has finite measure, right. So, this is the inner regularity. So, inner regularity on sets with finite measure. Sets with finite measure. And one more property, if E is in M and measure of E is 0, then A contained in E implies A also belongs to M. So, this is simply the completeness of M with respect to mu. Okay. So, the sigma algebra you get is a complete sigma algebra with respect to the measure mu. So, starting from a positive linear functional, one has a measure, positive measure mu defined on a sigma algebra slightly bigger than the Borel sigma algebra, such that we have 1, 2, 3, 4, 5 these properties. So, these properties resemble the properties which you have seen for Lebesgue measure, and whatever example we have seen earlier, right. So, look at f going to f of 0 for example, this gives me delta naught as the measure, and of course, that is a positive regular measure as you can see immediately. So, this is a rather major theorem, we will not prove this. So, I will refer the so for proof see second chapter of Rudin's real and complex analysis. Okay. It is a rather long proof, we will not prove this, but we will look at the consequences. So, maybe let us stop here. So, starting from a locally compact Hausdorff space and looking at the linear functionals there, what we have done is to state the Ries representation theorem in full, which says that all positive linear functionals are given by integration against positive measures. Now we will look at some consequence. So looking at the properties of the measure and the sets, you see similarities between Lebesgue measure which we have encountered before. So we will continue that. So think of these results are results in the abstract settings which are analogous to whatever you know for sets in Rn. We will continue this for a while and then use the Riesz representation theorem to construct the Lebesgue measure. Okay, so let us stop now.